Let's take a look at the buck boost converter now. This DC-DC converter also has two switches, S1 and S2, inductor L and capacitor C. The input is connected, the input is V in, voltage source, DC voltage source, and the output is the voltage across capacitor VO. R is the load resistance connected. Again, S1 is on and S2 is off for an interval of dTs, and S2 is on, S1 is off for an interval of 1 minus dTs. So if you look at the KVL equation in the first interval dTs, where S1 alone is on, VL is equal to V in, and in the second interval VL is equal to VO. By just looking at these expressions, we can say that for a circuit to operate in periodic steady state, the average value of VL, the average voltage across an inductor, should be 0. That means if V in is getting impressed across inductance, the inductor for an interval of dTs for some interval, if VO is getting impressed across the inductor for the next interval, they have to be opposite in sign. That means the polarity of V in and VO has to be different. For a positive input voltage, you will get a negative output voltage. That is one observation. Then the second observation is about the relative magnitudes of V in and VO. Since only V in and VO are getting applied across the inductor, a smaller voltage can be applied for a longer duration and a larger voltage will be applied for a smaller duration. Then volt seconds are balanced, right? So the duty ratio can be changed, as in the switch S1 can be on for a longer time or S2 can be on for a longer time. That means the magnitude wise, if you look at the magnitude, the output voltage can be more or less than the input voltage. That is why it is buck boost converter. Let us take a look at the waveform of inductor voltage VL. Because looking at this voltage waveform and applying voltage volt second balance, it will help us arrive at the relation between the average output voltage and input voltage. That is why we are looking at the waveform of the voltage across inductor. So it is V in for dTs and VO for 1 minus dTs. Remember, we have applied the small ripple approximation. That means the ripple component in output voltage VO is ignored. So V in dTs plus VO times 1 minus dTs will be 0, and the relation between VO and V in can be given by VO by V in is equal to minus D by 1 minus D. And again, the duty ratio is less than 1, because D is equal to 1 means always S1 is on, the output is never connected to the input. So things just stay there. As far as output is concerned, the capacitor has 0 voltage, it will remain at 0, but the inductor current will keep on increasing because we have a direct voltage source connected across it, and it will destroy. So D is equal to 1 is not really an operating point. And how about the inductor current waveform? And why do we need the inductor current waveform here? Because if we want to plot the waveform of output voltage, we need the capacitor current waveform so that we can integrate. But the capacitor current waveform can be obtained by KCL along this node, at this node. And if you want to apply KCL at this node, you need to know the switch current IS2. And if you need to know the switch current, you need to know the inductor current, because the switch current is equal to inductor current in the second interval. So the inductor current will rise when the voltage across inductor is positive. In the first interval dTs, VL is equal to V in. So the voltage across inductor is constant and the current will rise starting from some initial condition. And the rise will be linear. And again it will fall in the second interval. It will fall to the same point because we are in periodic steady state. So the peak to peak ripple in inductor current can be easily calculated as delta IL by dTs is equal to V in by L. In the first interval, if you apply this, V is equal to L di by dt. and delta IL will turn out to be V in times dTs by L, or minus VO times 1 minus dTs by L, because we already know the relation between V in and VO. But how do we get the average value of inductor current IL, capital IL? For that we need to apply KCL at node B, and if you apply KCL, we observe that IN is equal to IL plus IC plus IO. And if you integrate on both sides from 0 to Ts and divide by Ts, we see that one term on the right hand side becomes 0. Why? Because the average value of capacitor current IC should be 0 in periodic steady state. That gives us that the average value of input current IN, that is nothing but the switch current, S1 current, is equal to IL minus IO. Average value of IL minus average value of IO. And what is IO? IO is the average output current, which is the average output voltage VO divided by R. So if we know IN, the average input current, and average output current, we can calculate the value of average inductor current. And how can you find out the average input current? By power balance. Pin is equal to PO, the average input power is equal to the average output power, because we are assuming system to be lossless, the DC-DC converter to be lossless. So V in IN is equal to VO IO, and the input current, the average value of input current will be minus D by 1 minus D times IO. So that gives us the expression for the average value of inductor current IL as minus VO by R into 1 minus D. How does the capacitor current look like? The capacitor current is equal to minus VO by R in the first interval, and since VO is almost constant according to our approximation, and it is negative as per the derivation that we have done for a positive V in, so IC will be positive. The capacitor current will be positive in the first interval. In the second interval, it is minus IL minus VO by R. So it is the negative of IL with VO by R being subtracted, the average output current being subtracted, and that is what is shown in the second interval here. Again, it will be negative, it has to be negative in this interval because the capacitor current was positive in the first interval, because the area under these two waveforms of capacitor current, the positive part of capacitor current and the negative part of a capacitor current, have to be the same for the charge balance to be true. We are ready to plot the output voltage waveform now. So it will be an integral of capacitor current, again starting from an initial condition. It will rise in the first interval and it will fall in the second interval, and it will keep happening. What is the peak to peak value of the output voltage delta VO? It is equal to the charge gained by the capacitor in the first interval, or the charge lost by the capacitor in the second interval, divided by the value of capacitance C. So looking at the first interval, the capacitor current is minus VO by R, and minus VO by R times dTs will be the charge, and divided by C will be the voltage ripple at the output. And what is our small ripple approximation? Our small ripple approximation is delta VO by VO is much less than 1. That translates to, again, the switching time period Ts being much smaller than the time constant RC. So as long as this time constant is much larger, RC is very long than much longer than the time switching time period, our ripple approximation holds good, small ripple approximation holds good, and this analysis is valid. We already have derived the expression for average output voltage VO. It is minus D by 1 minus D times V in. For a positive input voltage, we actually get negative output voltage, so it should be minus VO if we are plotting this way. So we have looked at the output voltage waveform and its average value. And how does the input current look like? Because we are interested in the input current also, the current drawn from the DC source also. We want it to be ideally a constant. But the current drawn from the source I in will turn out to be pulsating in this case, because it is the current through the switch S1, and I in is equal to IL in the first interval. In the second interval, I in is 0, and that is what is shown in this pink color waveform. The average value of input current has already been calculated by using power balance earlier. Now we'll look at how to replace these generic switches S1 and S2 by MOSFETs and diodes. For that, we need to look at the voltage blocking and current carrying capabilities. If you look at the first interval, when S1 is on, the switch current IS1 is equal to IL, and IL is greater than 0 in our case because the input voltage is greater than 0. And when S1 is off, what is the voltage across VS1? That is in the second interval. When S1 is off, VS1 is equal to V in minus VO, because S2 is on. And since V in is greater than 0, VO will be less than 0. So the switch S1 will be blocking a positive voltage with the indicated polarity. So switch S1 is conducting positive current and it is blocking positive voltage. So a MOSFET would be ideal because it can conduct in this direction and it can block positive voltage with that polarity. So S1 can be replaced by a MOSFET. Let us look at S2 now. S2 is off in the first interval and the voltage across S2 is given by minus V in minus VO. Sorry, it's a mistake. So it's minus V in plus VO. Minus V in plus VO. Since V in is positive, VO will be negative. So the voltage across VS2 is negative with the polarity indicated. And when S2 is on, in the second interval, IS2 is equal to IL. So IS2 will be conducting, it will be taking over the current through inductor, and IL is positive, so IS2 is also positive. That means switch S2 has to conduct in this direction and block a negative voltage with this particular polarity. So a diode would be ideal for S2. One can also have a MOSFET with the reverse conduction property being utilized. But the simplest would be to have a diode, because the diode will take over immediately the current without any extra control given. So that is how we realize switches in a buck-boost converter, and similar methods of steady state analysis can be applied to include non-idealities such as the resistance of the inductor, or the equivalent series resistance of capacitor, or the voltage drops across S1 and S2.